So the first step we're interested in is drawing the VM diagram for this. And this will be useful because this will feed into the second part of what we're interested in, is then going to be looking at the stresses in the beam. So we want to start at statically determinant. It has a pin at A, a roller at B. So we can solve for the external reactions A and B in our beam here. We have a distributed load, 400 pounds per foot over 6 feet, which we can simplify on the external diagram to 2,400 pounds. And then a point load of 900 pounds as well. Again, for these problems, I can ignore what's happening in the, what I'm calling the x direction, because these problems feature no normal forces along the length, or no internal normal forces. So AX would be 0 anyway. So I'm just concerned about the vertical reactions and couples from my external connections here. All right, so solving forces in the y direction, solving moments around a point. I can solve for the external reactions A and B. A being 1,900 pounds up, and B being 1,400 pounds up as well. With the reactions known, now we can take this and create our loading diagram. And on the exam or on quizzes, I want, when you make VM diagrams, make sure you start with the loading diagram on top, then drawing your V and your M diagrams below it. At A, we found that we have that reaction of 1,900 pounds. Now, if you go back in our loading diagram to the original picture, we do have to represent this as our distributed load. ,400 pounds per foot. And then at B, we have the other reaction of 1,400 pounds. Everything, all of my forces are in pounds here, so the internal shear force V will also be measured in pounds. And I want to add, where I have this point load, that extra line there. So I remember to stop there because I'm going to have an instantaneous change in my V diagram. I have a distributed load pointing down, so right away I want to find the area under it, because that will help me draw that part of the V diagram also. Right, so now I just follow my loading diagram to draw my V diagram. I have to see what's happening on the lines and between the lines for instantaneous changes and gradual changes in the value of V. So at the extreme left, I'm starting at 0, and immediately I go up by 1,900 pounds because of that point load pointing up. And I see between this line and the next line, I do have a distributed load. So by the time I get to the next line, I'm going to lose 2,400 pounds from the value of V. So if I'm at 1,900 and I lose 2,400, I'm going to go down to -500. This is a horizontal line. I'm integrating when I go draw my V diagram, so the order of the line goes up by 1. So therefore, this is connected by a first order line, which is just a straight line. I'm on the line here. I'm at -500. I'm going to go down by another 900 on the line. Which will take me at -1,400. Between the lines, there's no loading, so I remain at -1,400. And then on the line, I have a vertical force up of 1,400, which will take me back to 0. Right, start at 0 and end at 0, so I can be relatively certain my V diagram is correct here. On my V diagram, I had this 0 crossing, so that will become either a max or a min on my M diagram, so I want to add that extra line going down so I know I stop there when I'm drawing my M diagram next. And before I go and proceed to draw my M diagram, I want to find the areas under the V diagram between lines, which will help me in the M diagram step. So here I have a rectangle that's negative 1,400 by 3 feet. And it's all below zero. This has an area of negative 4,200 foot-pounds. So I first have to find where does that zero crossing occur. And say that 1,900 to x is the same as 500 to 6 minus x. So the ratio of their sides are going to equal the value of x is here. Solving this for x, x is 4.75. So the area under the smaller triangle, rounded off, will be negative 313 pound-feet. And then this triangle will be 1,900 times 4.75 over 2 will be 4,513 positive pound-feet. Now, if I look at my loading diagram, I don't have in this problem any point couples or point moments, so I won't have to worry about any instantaneous changes in my M diagram. All of the changes in M will come from the integral under the V. So on the line, I won't have anything happening in my M diagram. So between the first line and now what I know is going to be a maximum value, I'm going to increase my value of M by 4,513. This is a first order line, which I'll mark here. So when I integrate, it becomes a quadratic, which can be either concave or convex. So either this is going to be connected upward or downward like this. So I have to determine that by looking at the value of V to make my sketch. The value of V is the slope of M. So the slope of M starts at 1,900. And then the slope of M stops at 0. So that tells me the concavity of how to connect my M diagram together. Again, I will mark this. This is a second order curve. $513. By the time I reach the next line, I'll be going down by 313, which will take me to 4,200. Again, the value of V is the slope to use. Again, a second order curve. I'm going to start with a slope of 0 since that's the value of V. I'm going to end at a slope of negative 500, which means that's the proper concavity for this section. So from a 0 slope to a negative slope gives me that concavity. And finally, I'm at 4,200, and by the time I get to the last line, I'm going to draw by 4,200, which takes me back to 0. This is horizontal, which means when I integrate it, it becomes a first order line. And I want to denote it as such.